So when we looked at the growth of a single population, we said dx dt is a function of x, and we had exponential growth, logistic growth. Now we're going to have two interacting populations, x and y. So x somehow, so there are different models for this, there are different processes. There's the process of competition. That means x and y compete with one another. There's a process of predation. There's also a process of mutualism. Those are the most obvious ones. So competition, the presence of the other population affects the growth of the current population. So x, the growth of x will decline if y is there, and the growth of y will decline if x is there. In predation, if y eats x, then the growth of x will go down as y goes up because there's more predation pressure. However, the growth of y will go up with x because there's more food. And in mutualism, they both enable one another. Can anybody think of how mutualism can arise? Yeah, so how might that arise? Right. So sometimes it's just a one-directional relationship which is called amensalism. That is, if there's a fish that eats the algae off a tortoiseshell, well, there's some fish that feed on the teeth of other fish, little fish. Then the more of the big fish around that little fish can clean, or for example, some birds, like oxpeckers, eat parasites off big animals. And the more, let's say, buffalo that are around, the oxpeckers do better because there are more places where they can find parasites. That's kind of one direction, but it goes in both directions. So maybe population A makes something of advantage to B, and B makes something that A needs. So you find this in economics quite a lot. Two businesses, they depend on each other for products, and so I need a particular product that you make, and you need a particular product that I make, so we kind of feed on each other and both do better. Okay. So when we write models of a general nature, we can write them in two ways. We can write dx dt is some function of x and y, and dy dt is another function g of x and y. So here I call this capital F and capital G, and the reason why I do that is that I want to discriminate between two kinds of functions, or two kinds of models. This model says the total growth rate is a function of x and y, and this model says the total growth rate of y is a function of g of x and y. So here I'm talking about total growth rate, total growth rate. But if you remember, we had a model that looked like this. dx dt equals r times x, and we call the r the per capita growth rate. And then we said maybe r can be written as little r 1 minus x upon k. So in other words, big R goes down linearly with x. If we wrote that down, we would get that dx dt is equal to r 1 minus x upon k, and then we multiply that by x. So I'm going to put the x in front there, so we recognize that as a logistic equation. In the same way, I could say this is equal to x times some function of x and y. So now I'm saying that the r depends both on x and y. And just to make sure I don't get confused, I'm going to use a lowercase f here as my per capita growth rate. And over here, I'm going to write y is g of x and y. So if I write down the model like this, then it's each population has a per capita growth rate. And instead of the per capita growth rate being constant, the per capita growth rate is a function of both x and y. Here, the per capita growth rate is written just as a function of x, and I get the logistic equation. Here, I write the per capita growth rate as a function of x and y. And you'll see that based on the form of these functions, I can describe processes that are called competition, or processes that are called predation, and I write down what's called a prey-predator equation. Or I can write down equations that reflect mutualism, but I'm not going to actually write those down. We're going to focus on both competition and predation. And we're going to say, how do we analyze these populations? Because an equation like this, we saw we could integrate. But in general, when we've got a population model like this, where the right-hand side has x and y intertwined with one another, there's very often no way to integrate it, so you can't just solve it. So here's where NOVA becomes particularly useful, because you can always numerically generate the solution. But sometimes we want to understand the qualitative aspects of the solution. So we're going to discuss a technique for understanding the qualitative components of the solution, which is called phase plane analysis. But before we do this phase plane analysis, let's think about these processes. So if I've got a process that I call competition, what does competition really mean? Competition means that the function f, is the function f going to increase or decrease with y if x and y are competing? So as the density of y increases, what will happen to the per capita growth rate of x if it's competing with y? It's going to decrease. So it's going to become more and more difficult to grow as more and more of your competitors are out there. So how would we write that mathematically? So we would write the derivative of f with respect to y is less than 0. That's competition. And similarly, if x and y are competitors, then y is competing with x and x is competing with y. So here I've got the equation for y and the per capita growth rate of y. And then I say the per capita growth rate of y is going to decrease as x increases. So df dx is less than 0. And I call this inter-specific competition. So that means between the two species. When we write down equations like this, we sometimes call the species x and species y. It doesn't have to be biologically different species. Very often it can be, but you can just say type x, type y, if we're not dealing with species, but very often it's just, the generic term for this is called interspecific, but it might be competition among types or competition among species. Now, if there's density dependence of this type as well, so that means there's competition within the population. So this is competition within the population. Then what would happen is that with increasing density of x, the per capita growth rate goes down, as it does here. So then if we said df dx is less than 0, and this is dg dx, and dg dy is less than 0, then that's intra-specific competition. So this means the growth rate of x decreases with increasing y. The growth rate of y increases with increasing x. The growth rate of x decreases with increasing x, and the growth rate of y decreases with increasing y. So these are what the form that you'd expect if you're looking at competition among the two species or competition within the species. Does everybody understand that? Now we can do the same for predation, where x is the prey and y is the predator. So if x is the prey, the growth rate of the prey, df, with respect to the predator. So how is f going to be affected as the predator increases? So if this is predation, you expect the growth rate, the per capita growth rate of the prey to decrease as the predators increase. Because that's bad news for the prey. There are more predators out there to eat them. So they're going to grow more slowly. And maybe they'll even start declining. So that means f is going to decrease as y increases. Because f is the per capita growth rate of the prey. And as the predators increase, so the prey per capita growth rate must go down. So that's the f dy is less than 0. On the other hand, the g dx, you have predators growing per capita growth rate. And as the amount of food, which is x, increases, so there's more resources for them to grow on, so you'd expect the growth rate to go up. So you'd say dg dy is going to be greater than 0. And so you'd have this situation. And then you can make maybe there's intraspecific competition. So within species, individuals are still competing among each other. But among species, you get this asymmetry, where it's bad news for the prey if the predators go up, but it's good news for the predators if the prey go up. And so you can also do for mutualism. But mutualism can be more complicated. So sometimes you get interactions where at low densities, you can get a mutualism, but at high densities, you can get competition. So for example, if at low densities, individuals are producing things that are useful to the other, but at high densities, they're both competing for space, then it becomes more complicated. And so mutualisms are generally like that. At low densities, you can get mutualisms, but at high densities, things usually go wrong. At high densities, for example, populations they pollute the environment in one way or another, or they degrade the environment in one way or another. And as densities get very high, so the environment becomes more and more degraded. So you'd say there was a mutualism between humans and cattle, in the sense that the more cattle there are, the less likely it is that humans will starve. And the more humans there are, the more likely they'll invest in building things for cattle to roam around, and they're more likely to domesticate cattle or to get involved in husbandry and things like that. But then at high densities, cattle and humans are competing for space on the landscape. Yeah? Yeah. Yes. dg is the growth rate of y. So I would say, what about the f dx? Well, we're going to have some models where the f dx is 0, and we're going to have some models where the f dx is less than 0. So there's intraspecific competition, and this could be competition or predation for them. But the fact that this is positive tells me, when I look at these two, it's predation, as opposed to, so it's the two together that tells me this is competition, this is predation. So this could be competition or predation, but it's predation because of this. Over here, what's happening within a species? So it could be, let's say, generally, it's something like this. But if there could be social forces that say that the growth rate of g or the growth rate of x, of f, remember we talked about this Lee effect, and so at low densities, as the density increases, everybody does better because there's social effects. So it may be that this could be one sign at low densities and another sign at high densities. So this could be the f dx is greater than 0 at low densities of x and less than 0 at high densities of x. And that would reflect the fact that the species is social. So what I'm trying to look at here is what I call pure competition, pure predation. And then here, this reflects that within species there's still competition, but between species there's predation. Here within species there's competition, and between species there's competition. Okay? And we're going to look at specific models of these two things. Now, when I analyzed an equation like this, the f dx, the x dt equals f of x, and I said, okay, how do I find out what's going on? Well, the first thing I said, I could look for the equilibria. So I could solve the equation fx equals 0, and that would give me the equilibria. And there may be more than one solution to that equation. So for example, in the x dt equals ax 1 minus x upon k, then fx equals 0 implied x was equal to 0 or x was equal to k. And then I could say, what's the next thing I found out about this? The next thing I found out is which one of these, are they stable or unstable? And I would find out, well, this is unstable, this is stable. So as long as I start out from some initial condition greater than 0, I would go to this one and move away from that one. So that's how I found out about this model in particular. But the general procedure when you have a system like this is find the equilibria and characterize their stability properties. Okay? So what's the general procedure for an equation like this? So you could say the general procedure is the same. Find the equilibria and characterize the stability properties. This is pretty messy. So let's write this down. dx dt equals fxy, and dy dt equals gxy. So how do I find the equilibrium of the system, or the equilibria, because there may well be more than one? What equations would I solve? What do you think? Well, by definition, an equilibrium is where both x and y are unchanging over time. So I would solve for the equilibria. I would solve fxy equals 0 and gxy equals 0. If that's an equation, that's two equations in two variables, in two unknowns. But it's not a linear equation, it's general. If it were linear, if f of x, y, were equals ax plus bx plus by plus c, and if gxy were dx plus ey plus f, then if I solved these equal to 0, I would get two equations, two linear equations in two unknowns, which has one solution. But in general, I'm not going to get linear expressions, I'm going to get nonlinear expressions. So if I had a quadratic expression in there, then I might get more than one solution. And that's what I would solve. So you can solve for the equilibria. However, if I just look at one of these, fxy equals 0, and I said, what does that represent? So let's say fxy was equal to something like ax minus bxy. Then if I said fxy equals 0, then if I had to solve this, I would say ax equals bxy. So either x equals 0, or if x is not equal to 0, I can divide it out, y equals a over b. So if I were to look in the xy plane, then I would get either x equals 0, which would be this line, or y equals b over a, which is that line. So I get two lines. Now this is a very simple example. In a more complicated example, I wouldn't necessarily get two straight lines, but I might get some curves. So what I'm saying is that fxy equals 0 is a curve in xy space. So for example, if f of x, y was equal to ax minus bxy minus cx squared, then fxy equals 0 would be x equals 0, or a minus by minus cx equals 0. And now if I solve this for y in terms of x, I would get by equals cx minus a, and I can divide through by the b, and that would just be a line of some slope. Yeah? This line here. Okay, so that's a over b. But the point is that now, by setting this equal to 0, I get some equations, and these equations represent lines in this case. But if they were more complicated, for example, if this were x cubed instead of x squared, then this would be a square here when I divide out by x, either x equals 0 or it's equal to that. And then I would get squared over here, and that would be a parabola. So the main point is that a relationship like this, you have a two-dimensional space. And here you have a two-dimensional function that constrains the relationship by one equation. So if you've got two dimensions and one constraint equation, then you get a one-dimensional object, and that one-dimensional object is a curve in two-dimensional space. Okay? So when I do this, I find what are called the null isoclines. Or it's just called the nullclines. Now the word isocline, cline is slope, and iso means same slope, and null means the slope is 0. So if I've got two